Hi everyone, thanks for coming, and I will now present my lab 3 report. This lab consists of two parts. So in part 1, we will calculate an unknown mass of black hole at origin based on the trajectory of a star orbiting it. So the concept we use is still Newton's second law. We want to calculate the Fnet on the start, and then based on the formula of the gravitation here, if we get the Fnet, which is just the gravitation of on the star by the black hole, then we can rearrange this formula in this way and then get the mass of the black hole with the information we know. And we also use some formulas for visualization, that is the parallel and perpendicular component of Fnet. And here's our model. The free-body diagram of our model is that the star is here and the black hole is here, and the black hole will apply a gravitation on the star. And by Newton's third law, the star will also apply a gravitation on the black hole, but this is not our interest. And the gravitation can be split into parallel and perpendicular part. So for our computational model is given here, which is basically implementing the idea of the formulas, which will have our P initial, P final, and this is the most important part that calculate our Fnet based on the change in rate of change in momentum. And here's how we calculate the perpendicular things. So as the final result, we will get the mass of a black hole to be equal to 1.487 E plus 34, and this is the average of all iterations, like that. So then we want to know how the net force and rate of change in momentum are different. Actually, they are the same, and this is given by the Newton's second law. And consequently, the parallel and perpendicular components of the change in momentum and force are the same, because they are both defined from the defined on the direction of the movement. So now let's talk about part 2. So in part 2, we want to build a model to find the interaction of gravitation among a black hole, planet, and a spaceship. And with this model, we want to find the initial velocity of the spaceship such that it gets as close as possible to the black hole without crashing into it. So it still uses the formula for gravitation, but we use it directly now as we know the mass of both objects. And the R hat here, I want to point out it will point from the source of the gravitation to the object of our interest. So here's our model here. So you can see the black hole here, our planet and spaceship. So on the spaceship, you will have a gravitation that is from the black hole from the black hole on the spaceship and from the planet on the spaceship. And we also want to model the movement of the planet. So it will also have gravitation coming from the other two things. So the computational model for this one, for part 2, is here. So we calculate the Fnet on planet and Fnet on ship separately, and the Fnet on planet consists of two parts, that is coming from black hole and coming from ship. And in this, we just apply the formula of the gravitation, and the same thing here. And then we apply the velocity and position update formula to update the position of the ship and planet. And after this model, we can then try to find out the result, to find out optimal result by a lot of trial and error. So in the end, I find out the best initial velocity is given by this number here. So this number by putting this number into our program, I will get a trajectory like this that it almost gets as close to the surface of the black hole without crashing. So then what if we want to enter the orbit of the black hole without crashing? In this case, I think a way is to increase the y component of the initial velocity and decrease the x component of the velocity. But in this way, we may not get that close as that if we can leave the black hole. So we'll get into an orbit more likely like a planet around the black hole. So in conclusion, there are some possible sources of error from this lab. One is we are taking final velocity as our average velocity and initial momentum as our average momentum. Both of them are not very close to the actual situation. And there may be some floating point errors of Python in calculation, which I don't know. And in this lab, we basically applied the formulas of gravitation to model the interaction between planets, black holes, and spaceship. So from this, we gain a better understanding of the gravity rules. Thank you very much.